Hello, people, and welcome back to the Sleepy Science Lab, where the night is calm, the universe is wide, and curiosity drifts like stardust. Tonight, we're floating into the breathtaking world of solar systems, far beyond the familiar orbit of our own sun. Out there, hidden in the quiet dark, lie arrangements so strange and beautiful they almost feel like dreams painted in gravity and time. Every star is its own tiny universe, surrounded by companions of rock, ice, gas, rings, moons, and mysteries. Some of these systems glow with twin suns, others cradle molten worlds, and some hold planets that drift unbound through endless night. What we're exploring isn't just space, it's wonder itself, wrapped in the architecture of the cosmos. If you enjoy wandering through these peaceful corners of the universe, feel free to like, subscribe, or share a thought below. It helps more sleepy travelers find this little pocket of starlight. For now, take a slow breath, let the darkness settle around you, and let your mind relax as we begin tonight's journey. Let's start with a cosmic surprise. Some solar systems have planets that orbit two stars at the same time. Picture standing on a distant world, watching not one, but two sunsets glowing across the horizon. These are called circumbinary systems, where a planet loops around both stars in a graceful braided path shaped by shifting gravity. Despite the complexity, stability emerges when the stars and planet fall into just the right rhythm. From such a world, the sky would brighten and dim as the stars eclipse each other, creating seasons unlike anything on Earth. Scientists believe planets can still grow in these chaotic disks, pausing and continuing as waves of dust sweep through. These systems prove that where physics opens even the smallest pocket of order, nature builds worlds. But strangeness doesn't stop there. Some planets orbit in the opposite direction entirely. These retrograde worlds run counter to their star's rotation, as if rewinding the clock of creation. This backwards dance can begin when a passing giant tilts a young planet, or when gravitational scuffles twist a system out of alignment. The result is an orbit tilted, or even fully flipped. These strange geometries reshape a planet's winds, tides, and temperature cycles. They also act like cosmic scars, preserving the memory of collisions or close encounters that happened billions of years ago. Each retrograde orbit is a quiet piece of evidence from a long-forgotten drama in space. And here's a comforting thought in the middle of all this vastness. About 1 in every 5 sun-like stars may host an Earth-sized planet. When astronomers analyze dips in starlight and correct for viewing angles, a pattern emerges. Small, rocky worlds seem to be incredibly common. Some orbit in regions where liquid water might exist under the right conditions. It doesn't guarantee oceans or breathable air, but it transforms our search from hunting for rare miracles into mapping a neighborhood full of possibilities. As technology improves, we'll soon be able to read the chemistry of their atmospheres, searching for hints of clouds, winds, and maybe even life. The night sky suddenly becomes less empty and more like a sea dotted with countless tiny shores we haven't yet visited. Then there are the wanderers, rogue planets, drifting through the galaxy without a star. Cast out by gravitational chaos or never captured at all, they roam in eternal night, lit only by distant starlight and warmed by the faint heat left from their creation. Some may hide thick atmospheres or subsurface oceans, kept alive by their own internal energy. They're incredibly hard to detect, but occasionally astronomers catch their faint glow or notice a star briefly brighten as one passes in front of it. These These lonely travelers reveal that solar systems are messy places where not every world finds a permanent home. We'd even discovered solar systems almost as old as the universe itself. Born when the galaxy was young and rich with only a few heavy elements, these ancient stars still host planets. Their worlds have survived cosmic collisions, the birth and death of countless stars, and more time than our minds can truly grasp. If their atmospheres remain, they've endured climates and cycles spanning billions of years. Studying them opens a window into the earliest chapters of planet formation and shows that world building began nearly as soon as starlight first flickered across the cosmos. But planets don't always stay where they start. Over millions and billions of years, they migrate. Interactions with gas, dust, and neighboring planets can push them inward, outward, or into new orbits altogether. Sometimes a giant planet drifts toward its star, reshaping the climate of every smaller world nearby. This quiet shuffling explains why so many solar systems look nothing like ours. Planetary families are dynamic, sculpted by friction and gravity, and their final arrangements hold memories of ancient dances that played out long after their birth disks vanished. Some systems pack their planets much closer together than ours. Imagine several worlds all orbiting inside the distance of Mercury, each circling the star in days or weeks. These compact families look tight, but can sit in perfectly stable harmony. From the surface of one world, another planet might loom huge and bright in the sky, shifting phases in just a few days. Their tides, atmospheres, and seasons are shaped by their crowded neighborhoods. These systems reveal that nature sometimes prefers efficiency, building many medium-sized worlds instead of a few large ones. And the variety continues. Some solar systems form with no rocky planets at all. If the disk is poor in heavy elements, or if giant planets grow early and monopolize the material, the inner zones may stay soft and gaseous. These systems might be filled with Neptunes and huge gas planets, each shaped by heat from the star or deep cold far away. Without solid surfaces, their geology looks nothing like ours, but chemistry thrives in their clouds and on their moons. They remind us that Earth-like worlds aren't guaranteed, and that the universe experiments freely with its designs. Sometimes, planets fall into perfect harmony. Resonant chains lock worlds into synchronized orbits, where one planet might complete 2 laps for every 3 a neighbor finishes. This cosmic choreography can last billions of years if nothing interrupts it. During migration, the planets gently capture one another into shared rhythm, like dancers finding the same beat. Their transits reveal subtle tugs that help astronomers measure their masses and structures. From such a world, bright neighboring planets would drift across the sky on a schedule as predictable as music. And still, the surprises go on. Some solar systems are filled with planets all roughly the same size, a stark contrast to our mismatched family ranging from Mercury to Jupiter.
Where you can direct a voice, create realistic dialogue, and so much more. Edit these placeholders to get started.
In some distant solar systems, every known planet is strikingly similar in size, almost as if they were poured from the same cosmic mold. Instead of a mix of giants and runts, these families consist of tightly packed super-Earths or mini-Neptunes, each only slightly different from the next. Yet despite their shared scale, their personalities can vary wildly. A planet closer to the star might be scorched and stripped bare, while a sibling just a little farther out could be wrapped in thick clouds or layered oceans. This surprising uniformity hints at early conditions that divided material more evenly, or gravitational balances that prevented worlds from outgrowing one another. It's a quiet reminder that normal is a flexible idea in astronomy. The universe might love symmetry far more than we do, and such balanced systems tease the possibility that stability and life-friendly environments could emerge more often when no dominates the gravitational stage. Then there are solar systems where planets orbit so close to their stars that metal itself turns to vapor. These ultra-hot worlds complete a full year in days or even hours. Under their relentless suns, temperatures climb high enough to evaporate iron, rock, and minerals. Mountains may never form because the ingredients of stone simply sublimate into the atmosphere. Powerful winds sweep metal vapor from the scorching day side to the frigid night side, where it cools into glittering mineral clouds that could rain molten droplets back to the surface. These planets push chemistry far beyond anything we know on Earth, teaching us how atmospheres behave when heat crosses into extremes. Their very existence proves that planet formation doesn't shy away from the furnace, it adapts, creating strange survivors in places we once thought impossible. Other worlds lose their atmospheres entirely. Not every planet manages to hold on to a sky. Intense stellar winds and radiation can blast gases into space, stripping close-orbiting planets down to bare rock. Without an atmosphere, the day side bakes while the night side freezes in a harsh, silent duel of heat and shadow. There's no weather, no protection from meteoroids, and no medium for sound. Still, these airless landscapes act like perfect record keepers, preserving a planet's geological history without the erasing effects of wind or rain. By studying them, astronomers learn how atmospheres are lost, how magnetic fields shield or fail, and how delicate the balance of pressure and temperature can be. Even without air, these scarred worlds reveal powerful stories about survival. Other planets begin life far from their star and only later move inward. Where a world forms is not always where it ends up. In the cold outskirts of young disks, ices and dust can clump together more easily, building massive cores that eventually drift toward warmer regions. This slow inward journey can happen through gas drag or through gravitational nudges from neighboring worlds. A giant born in deep freeze might end up sizzling close to its star as a hot Jupiter, utterly out of place from where it formed. As it migrates, it can scatter smaller planets, sculpt debris, and lock survivors into resonant rhythms. By tracing these migrations, scientists decode the hidden past of systems that seem calm today. A planet's current orbit is just a snapshot, not a birthplace. Of course, not all solar systems survive forever. Some meet violent ends when their stars explode as supernovas. A massive star nearing death can erupt with a brightness that outshines entire galaxies for a moment. Shockwaves rip through nearby planets, stripping atmospheres, melting surfaces, or shattering worlds entirely. Even planets that remain intact may be sterilized by radiation so intense it rewrites their chemistry in seconds. The blast carves huge bubbles through surrounding gas, ending planet formation nearby, but potentially triggering it far away. Fragments of shattered worlds drift into deep space, becoming lonely remnants of a destroyed system. But even in destruction, a supernova spreads heavy elements that seed future stars and planets. Solar systems die, but their material is recycled into new chapters of cosmic history. Some exoplanets wear rings so massive they dwarf entire stars. Rings aren't just a Saturn exclusive. In a few extraordinary systems, ring structures stretch so wide that their total diameter exceeds that of a medium-sized star. These colossal halos may come from shattered moons, captured comets, or leftover debris that never merged into a satellite. When the planet crosses its star, the rings block light long before the planet itself appears, creating strange dips that first hinted at their existence. Their stability puzzles scientists because rings that large should quickly spread or crumble. Their persistence suggests recent cataclysms or ongoing processes that keep them in shape. If a moon forms within these rings, it may eventually carve out its own orbit and become a full-fledged companion. Even familiar features like rings can become epic in scale when time and gravity have space to play. Other systems contain moons larger than Earth. These aren't mere sidekicks, but full-fledged worlds in their own right, orbiting giant planets like miniature Earths tethered to colossal hosts. Such exomoons may sustain atmospheres, oceans, and active geology powered by tidal forces from both the planet and the star. Their cycles of light and shadow twist in unusual ways depending on their orbital dance. Detecting them is difficult because their signals blend with those of their planets, but faint timing shifts give them away. If confirmed, they would expand the idea of habitability to include not just planets, but their satellites. A moon with Earth-like mass, protected by a giant planet's magnetic field and warmed by reflected light, could be a surprisingly cozy home. On the other hand, some planets have no moons at all. These solitary worlds travel through space without even a small rock to accompany them. Their loneliness may come from violent early collisions that destroyed their satellites, or from placid births in regions too empty to build them. Without a moon, a planet's tilt can wobble over the ages, causing unpredictable seasons. Tides are weaker, shaping coastlines more slowly, and tidal heating inside the planet becomes minimal. Nights are darker, skies emptier. But these lone worlds offer clean laboratories for understanding geology and climate without external influences. Even the absence of a moon tells a story about scarcity, randomness, and the many paths a planet's history can take. Then there are the strange cases where moons form before their planets. A moon might begin life as an independent object in the swirling disk, or as a captured debris long before the main planet assembles. When the future planet gathers enough mass, it captures the older body into orbit. These ancient moons carry chemical fingerprints unlike their hosts, preserving a snapshot of early disk conditions that the planet itself never experienced. Their surfaces record impacts and radiation from eras before the planet even existed. These mismatched pairs show that order in a solar system is flexible, shaped by timing, capture, and chance. And here's a historic twist. The first exoplanets ever discovered weren't found around stars like our Sun. They were found around a pulsar, the dense, spinning remnant of a dead star. Pulsars emit radio waves with astonishing regularity. Tiny changes in the timing of those beams revealed the gravity of orbiting planets. These worlds survived or reformed after a supernova, enduring in one of the harshest environments imaginable. Their discovery shattered expectations and launched the entire field of exoplanet science, proving that planets can arise in places far stranger than our peaceful solar system. Finally, some planets orbit their stars faster than Earth spins once. These ultra-short period worlds complete a year in mere hours. Locked so tightly to their stars, they are tormented by intense gravity and blistering heat. Their atmospheres can boil away, shift into plasma, or churn in violent cycles. Tidal forces stretch them, melt their insides, and drive fierce volcanic activity. From the surface, the star would dominate the sky, and daylight would change dramatically in minutes.
Some planets out there refuse to play by the rules. Even when they stay tidally locked, with one side trapped in endless daylight and the other in permanent night, these blisteringly fast worlds still stretch our understanding of what stable orbits can look like. They remind us that the universe never stops testing the limits of what a planet can survive. And then there are the planets made almost entirely of water. Beyond our solar system lie worlds that are basically global oceans, with no continents and no dry land at all. Deep within them, the pressure becomes so intense that ordinary liquid water shifts into exotic, alien forms of ice like Ice 7 or Ice X, structures that don't exist naturally on Earth. Above these pressurized layers sits a thick atmosphere of vapor and steam, possibly wrapped in bright clouds that reflect starlight and give the planet a ghostly pale blue glow. Endless storms may sweep across oceans thousands of kilometers wide without a single obstacle to slow them down. If life exists in such places, it would have evolved in a world where land is nothing more than a myth. And if water worlds stretch your imagination, wait until you meet the diamond planets. Some exoplanets have densities and compositions that suggest they're rich in carbon that hardened under crushing pressure into vast layers of diamond. These sparkling worlds likely formed around stars that were themselves carbon-heavy, creating planetary systems where diamond is not rare but foundational. Beneath surfaces that could be scorching hot or freezing cold, enormous diamond mantles may extend for thousands of kilometers. These planets hold more diamond than Earth could ever dream of, transforming the idea of treasure into something cosmic and unimaginable. But the surprises don't end there. In some systems, planets orbit their stars in just a few hours. These extreme worlds race around their suns so quickly that a full year passes in the time it takes you to sleep through the night. The star-facing side becomes a furnace where rock vaporizes into clouds of mineral gas and molten metal rains back down as shining droplets of iron. Radiation blasts their atmospheres into shimmering comet-like tails that trail behind them as they whip around their stars. Locked, with one side eternally baked and the other forever frozen, these planets push physics to the breaking point. On the opposite end of the spectrum are planets so light and fluffy that they would float in water. Nicknamed superpuffs or cotton candy planets, these low-density giants have massive diameters but surprisingly tiny masses. Heated by their nearby stars, their hydrogen-helium atmospheres balloon outward until the whole planet becomes an airy, delicate sphere that could collapse from even a small change in radiation. Their very existence challenges everything we thought we knew about how planets form and survive. And speaking of giants, Super Jupiter suddenly seems small once you look at Super Jupiters. These massive worlds can be 10 or even 20 times heavier than Jupiter, yet still fall short of the mass needed to ignite into stars. Their gargantuan gravity shapes entire solar systems, dragging smaller planets into new orbits, disrupting debris fields, and sometimes preventing rocky worlds from forming at all. Some glow faintly with internal heat, while others drift in the frozen outskirts of their systems, colder than any temperature found on Earth. Some planets don't just orbit one star. They orbit 2 or even 3 at the same time. These circumbinary worlds travel around entire groups of suns, surviving in a gravitational dance so complex it feels like cosmic choreography. On their skies, multiple suns rise and set each day, their positions shifting as the stars orbit one another. Seasons and temperatures follow rhythms far stranger than anything Earth has ever experienced. And then there are the solar systems hiding inside star clusters. These clusters cram thousands of stars into a tight space, turning the night sky into a constant blaze of starlight. Astronomers once wondered if planets could even survive in such crowded neighborhoods where passing stars routinely tug at planetary orbits. Yet, some planets thrive there, holding on to their stars for billions of years, despite occasional close encounters that gently nudge their orbits. But solar systems don't always stay peaceful. Sometimes a wandering star passes nearby, its gravity acting like a cosmic hand that reshuffles entire planetary families. Worlds may be pushed into new orbits, frozen bodies might plunge inward toward their suns, and some planets may be flung completely out of the system to drift alone as rogue wanderers. These disruptions are rare in human lifetimes, but inevitable on cosmic timescales, leaving behind tilted planets and eccentric orbits as evidence of past chaos. Even the death of a star isn't the end of planet formation. When a star gently sheds its outer layers and becomes a white dwarf, it sometimes leaves behind a swirling disk of debris. From that debris, new planets can emerge. They're worlds forged from the leftovers of earlier planets, containing heavy elements that once lived inside the heart of a dying star. These quiet systems glow dimly, illuminated by the fading warmth of the white dwarf at their center. And in some places, solar systems are born from collisions between vast clouds of gas drifting through galaxies. When two clouds crash together, shockwaves compress hydrogen and dust, sparking the birth of new stars and planets. This chaotic beginning leaves behind systems with tilted orbits, unusual planetary spacing, and strange chemistry. Stars born from the same collision may travel together through space, each raising its own family of worlds. But not all solar systems reach completion. In many, huge clouds of dust never manage to form planets at all, lingering in space as reminders of what might have been.
Not every newborn solar system finishes the job. Some protoplanetary disks never solidify into planets, instead lingering as swirling halos of dust and gas for billions of years. These glowing clouds shimmer with starlight, frozen in the early stages of planet formation. Maybe the disk didn't have enough mass, or maybe disturbances in its youth prevented larger worlds from taking shape. Sometimes hidden planets lurk inside, guiding dust into rings and channels without ever clearing the disk entirely. These half-formed systems act like cosmic time capsules, preserving the raw ingredients of planet-making, long after neighboring systems have grown into mature worlds. Their drifting grains eventually return to interstellar space, ready to seed future generations of stars. By studying these suspended disks, astronomers uncover the delicate balance required for planets to fully emerge, and why some stars never get the chance to host worlds at all. Far beyond the warmth of their suns, some planets orbit in darkness so deep that their star appears as nothing more than a tiny bright point in the sky. Out here, starlight barely reaches them, and their surfaces plunge into unimaginable cold. Whatever atmosphere they once had may freeze into thick layers of ice, drifting downward in slow, ancient snowfall. Yet surprisingly, some of these remote giants may sustain subsurface oceans, warmed by internal heat left over from their formation, or by ongoing radioactive decay. Their orbits move so slowly that one full year can last thousands of Earth years. Entire civilizations could rise and fall before such a world completes a single trip around its star. These frozen wanderers show us that a solar system's architecture can stretch far into darkness, where endurance, chemistry, and deep internal heat take the place of sunlight. Not all planets stay aligned with their stars. While most worlds orbit close to the equatorial plane, some take on steep, tilted paths that hint at a violent past. Their odd inclinations may come from ancient collisions, gravitational nudges from passing stars, or twists in the disk where they formed. If life ever evolved on such a world, its seasons would be unlike anything on Earth. The star might rise in the far north for generations before drifting slowly toward the southern skies. Climate zones could migrate across continents in long, sweeping cycles. These misaligned orbits offer clues to forgotten upheavals, revealing the chaotic early history of their systems. Other planets stretch their orbits into extreme ellipses. Instead of the smooth circular journey Earth enjoys, these worlds swing from scorching proximity to their sun to frigid outer darkness. Such elongated paths often result from gravitational skirmishes with neighboring planets, close encounters with stars, or leftover turbulence from their system's birth. On the surface, the changes would be dramatic. At their closest approach, these planets may swell with heat, their atmospheres boiling with storms. But when they drift outward into the cold, that same atmosphere may freeze into frost or collapse into layers of icy haze. These wildly shifting seasons can crack mountains, churn oceans, and erase landscapes over time. Eccentric orbits remind us that even the rhythm of a year can be stretched and distorted by gravity. Some planets aren't just shaped by their stars, they're destroyed by them. When a world orbits too close to its sun, tidal forces begin tearing it apart. Rock and gas peel away, spiraling into space in long, glowing trails. Over millions of years, a once solid planet can shrink to a naked core surrounded by dust. Astronomers identify these doomed worlds by their debris streams, like cosmic breadcrumbs marking their slow unraveling.
These remnants may eventually become rings, dust belts, or raw material for new planets. It's a dramatic reminder that gravity can create and destroy with equal precision. Across the galaxy, some solar systems contain asteroid belts far larger than our own. While our belt sits quietly between Mars and Jupiter, other systems host belts hundreds of times more massive, filled with everything from fine grains to mountains of shattered rock. These belts may be the wreckage of worlds that never formed, or the remains of catastrophic collisions. For any nearby planet, the sky could glitter with constant streaks of falling debris. These belts preserve the chemical signature of their original disks, acting as archaeological layers for astronomers. They may even spread water and organic compounds to inner planets, helping seed the conditions for life. In some rare systems, the habitable zone isn't a single band, but multiple layers. This can happen around stars with broad temperature profiles, or in multiple star systems where overlapping heat sources create several regions where liquid water could exist. One band might host rocky planets with mild climates, while a second, farther out, could support gas giants with moons warm enough for oceans. These multi-zone systems dramatically expand the number of places life might emerge. And as stars age and brighten, these zones drift, giving planets temporary windows of habitability before conditions tip too hot or too cold. Stars also shape solar systems during their earliest moments. Massive nebulae glow with ionized gases, lit by the powerful radiation of giant young stars. Here, solar systems form in chaotic environments full of turbulence and violent energy. Worlds born in such an intense nursery carry the imprint of their birthplace. Rare metals from ancient supernovas, strange chemical cocktails from older stars, and scars from radiation storms that battered their surfaces when they were young. A planet forming in such a region would look up to a sky ablaze with red, orange, and blue clouds, lit by massive, brilliant suns. Planetary formation can even begin before a star is fully born. While the protostar is still gathering mass and has not yet ignited nuclear fusion, its gravity has already begun sculpting a disk of dust and gas. Tiny grains collide, growing into pebbles, then boulders, then the seeds of planets. Even as the protostar flickers uncertainly, these early bodies carve gaps in the disk and begin defining the future architecture of the system. The temperature, turbulence, and chemistry of this early phase decide whether the system will produce rocky planets, gas giants, icy worlds, or nothing at all. By the time the star stabilizes into steady burning, its planets may already be on their way to maturity. Some solar systems end up perfectly orderly, with planets neatly aligned in a flat plane that mirrors the gentle spin of their star. Others become chaotic mosaics of tilted, looping, and twisted orbits. In these unruly systems, planets may move at sharp angles relative to each other, orbit above or below the star's equator, or even circle in the opposite direction of the star's rotation. These strange patterns often come from ancient collisions, gravitational nudges from passing stars, or twists in the disk where they formed. The result is a map of every force that ever shaped the system, a cosmic memory etched into the paths of its planets.
By studying both the well-behaved and the chaotic, astronomers have learned something beautifully simple. The universe doesn't follow one blueprint. It embraces harmony and disorder with equal grace. A solar system can be peaceful and symmetrical, or tilted and tangled, and both versions fit perfectly into the cosmic design. Some planets never get the chance to finish forming before their star claims the leftovers. Planet formation is really a race between growth and destruction, and many worlds simply lose the race. As a young star ignites, its intense heat and radiation can burn away the final layers of the protoplanetary disk before all the would-be planets solidify. These incomplete worlds remain as oversized asteroids, scattered rubble piles, or lonely moon-sized bodies that never grow large enough to round into spheres or hold steady atmospheres. Their jagged surfaces still bear the scars of collisions that were never softened by gravity's gentle pull. Long after the gases vanished, these fragments drift quietly through space, frozen reminders of what might have been if time had stretched just a little longer. Studying these unfinished worlds shows just how delicate the timing of planet formation really is.
Even the most promising beginnings can be cut short when a star grows fierce too fast. Astronomers have also seen solar systems forming around baby stars. Protostars glow weakly as they gather mass and evolve toward true starlight. Around them swirl thick, luminous disks of dust and gas, warmed by the young star's gentle energy. Inside these glowing rings, telescopes have detected the unmistakable gaps carved by growing planets. These newborn worlds may still be molten, armored in hot ices, or wrapped in dense nebular atmospheres. Everything is shifting and alive, dust spiraling inward, ice giants chiseling bright channels, gas clumping into the raw ingredients of weather, oceans, and skies. Observing these systems in real time is like watching a time-lapse of our own solar system's childhood. Every snapshot captures a moment from a chapter we'll never witness firsthand. Each telescope shutter preserves a tiny piece of the cosmic story that shaped our home long before Earth existed. But not all stories end in creation. Some solar systems display unmistakable evidence of total planetary destruction. Astronomers have found glowing rings of metallic dust, white dwarfs contaminated with iron and silicon, and clouds of vaporized rock orbiting perilously close to their stars. These are the shattered remains of planets torn apart by tidal forces, consumed during stellar expansion, or smashed to pieces by ancient collisions. Even tiny fragments, from moons to pebbles, can survive long enough to outline the ghost of a once thriving system. Planetary destruction on this scale reminds us that solar systems are temporary arrangements. Their histories include birth, evolution, collapse, and erasure. Yet even in ruin, these remnants enrich space with raw materials that may one day form new worlds. The atoms of lost planets flow forward into the next generation of stars. Some solar systems even form near the galactic core. This region isn't empty, but packed with stars, gas, dust, and intense gravitational forces. Solar systems born here experience a wildly different environment from our quiet suburbs of the galaxy. Young stars in the core may be blasted by radiation from nearby supernova, or tugged around by the gravitational pull of passing neighbors. Their disks are loaded with heavy elements from older exploded stars, allowing planets to form quickly with dense metallic compositions. If these planets survive long enough, they may grow thick, exotic atmospheres or compressed heavy cores shaped by constant gravitational disturbances. And if life appears, it would evolve under a sky crowded with bright nearby suns, instead of the sparse constellations we see on Earth. These systems prove that planet formation can thrive even in the busiest corners of the cosmic city. Some planets take complexity even further, with atmospheres made entirely of vaporized metals. On ultra-hot exoplanets, temperatures soar so high that sodium, magnesium, and even iron vaporize into gas. These metallic atmospheres gleam like molten mirrors, scattering and bending light into vibrant spectral signatures that astronomers detect from light years away. Fierce winds sweep the metal vapors from the blistering dayside to the frigid night, where they condense into glittering clouds or fall as molten rain. Lightning flashes through metallic haze, creating a sky unlike anything we've ever seen. These shimmering worlds push the concept of an atmosphere to its absolute limits, proving that even metal can behave like air when the heat is high enough. And in some places, it isn't just metal in the sky, but crystals. There are planets whose atmospheres contain exotic silicates and minerals that condense into glass instead of water. Powerful winds fling molten particles high above the surface, where they cool into sparkling grains of glass or precious gems like corundum, the mineral behind sapphires and rubies. When gravity reclaims them, these crystals fall as glittering rain that scours the surface or bounces across oceans of liquid metal. Here, weather becomes spectacle. Storms can carve landscapes or decorate them, turning danger into breathtaking beauty. These shimmering worlds remind us that the universe loves to remix familiar elements into unimaginable forms. Some solar systems contain tidally locked planets, worlds where one side eternally faces the star while the other lies in endless night. This happens often around cool, dim stars where gravitational tides act quickly. The day side bakes under endless light, while the night side freezes toward absolute zero. Between them lies a twilight ring where violent weather circulates heat and gases in constant loops. Oceans might cling to this narrow band, and any life that emerges would grow under a sky where the star never rises or sets. Tidal locking challenges our assumptions about what a habitable world can look like. But models show that with the right atmosphere or oceans, these strange worlds could be surprisingly stable and even welcoming. Some planets push physics further. A handful spin so rapidly they begin to bulge at the equator, stretched almost to the point of tearing apart. These speed-spinning worlds complete a full rotation in only a few hours, whipping their atmospheres into colossal storms and flattening their shapes into squashed spheres. Gravity grows stronger at the poles and weaker at the equator, creating dramatic differences in temperature and pressure. If they rotated any faster, they would fling material into space. Their furious spin hints at violent histories, perhaps ancient collisions or gravitational slingshots that set them spinning like cosmic tops. Other planets dazzle in a different way. They reflect so much starlight they shine like mirrors in the dark. Their brightness may come from cloud decks filled with tiny crystals, from reflective mineral hazes, or from surfaces melted into glossy glass by relentless heat. As storms evolve and clouds drift, their brightness flickers, giving astronomers clues about wind speeds and atmospheric layers without ever seeing the surface. Some orbit so near their stars that their reflective coatings are constantly melting, vaporizing, and forming again. Others shine from layers of ice or salt that blanket their cooler surfaces. Each one becomes a natural beacon, sending its chemistry outward in shimmering pulses. But not every planet circles a sun. Astronomers have discovered worlds drifting alone through space, unbound to any star. Some were flung away during early chaos, while others may have formed on their own. Without sunlight, they glow faintly with leftover internal heat, their landscapes lit only by the dull warmth rising from below. Their atmospheres become slow, heavy blankets, trapping whatever energy remains, while the surface freezes into dark plains of ice. Deep beneath, pressure may preserve hidden oceans warmed by radioactive heat in the rock. These worlds are nearly invisible, discovered only when their gravity briefly bends the light of distant stars. Some glow weakly in infrared, like embers drifting through a cosmic night. They remind us that planet formation is messy, and that the galaxy is filled with lonely travelers carrying their shadows with them. Finally, theory predicts that some worlds may be built from exotic forms of matter. Most planets we know contain rock, ice, or gas, but under extreme pressures and unusual chemistry, matter can transform into states rarely seen elsewhere. Deep inside such planets, carbon may crystallize into massive diamonds, or hydrogen may compress into metallic oceans that behave like seas of electric fluid. Some models even suggest ultra-dense forms of matter that pack enormous mass into tiny volumes. These worlds would be small, heavy, and incredibly gravitational, swallowing incoming meteoroids with barely a ripple. They are reminders that the universe still holds secrets we haven't yet learned how to imagine.
Some worlds may form in places shaped by ancient supernovas or near compact stars where tides and pressure squeeze matter into extraordinary states. We haven't seen these places up close, but the way they tug on nearby stars, bend light, and disturb their surroundings hints that nature's methods for building planets stretch far beyond what we see in our quiet corner of the galaxy. Astronomers have even caught stars in the act of eating their planets.
As a star ages and expands, it can swell large enough to brush against a nearby world. When that happens, gas from the planet spirals inward and leaves unmistakable fingerprints inside the star. Suddenly, the star shows strange enrichments of elements like lithium and iron, ingredients that normal stellar fusion cannot create. Some stars even spin faster than they should, as if a swallowed planet delivered a final burst of momentum. White dwarfs tell similar stories. Their thin atmospheres should contain only pure hydrogen or helium, yet many show traces of heavy elements. The only explanation is a constant drizzle of planetary debris falling in, asteroids, broken worlds, and dust from shattered orbits. Infrared glows from hot debris rings and irregular dips in starlight tie the story together. Planetary death isn't one event, but a whole menu of endings. Gravity eventually reclaims everything it once allowed to roam. Some planets go the opposite direction and grow magnetic fields far stronger than Jupiter's. Inside these giants, roaring convective layers and fast rotations act like colossal dynamos, spinning up magnetic shields powerful enough to sculpt space itself. Charged particles slam into their poles with such force that their auroras can outshine the star in radio wavelengths. Bow shocks form where the stellar wind hits the field, while magnetic tails stretch for millions of kilometers. These supermagnetized worlds reveal what lies beneath their clouds. A field that strong hints at metallic hydrogen, salty oceans deep underground, or massive conductive cores. When such a planet swings close to its star, magnetic interactions can heat its upper atmosphere and shift the color of its auroral glow. By listening to its radio murmurs and watching its ultraviolet flashes, astronomers learn to weigh the hidden hearts of distant worlds. Other solar systems surprise us with not just one asteroid belt, but several. These belts form stacked rings of leftover building blocks, each with its own temperature and chemistry. Warm inner belts hold rocky debris, while colder outer belts contain ices and organic-rich fragments. The gaps between them aren't mistakes, but signatures of unseen planets clearing paths or locking dust into rhythmic patterns. Every belt is an archive, a timeline of interruptions, collisions, growth spurts, and stalled worlds that never fully formed. Dust smashed from countless impacts glows in infrared, outlining the architecture like chalk lines etched into the dark. Some planets go the opposite direction and grow magnetic fields far stronger than Jupiter's. Inside these giants, roaring convective layers and fast rotations act like colossal dynamos, spinning up magnetic shields powerful enough to sculpt space itself. Charged particles slam into their poles with such force that their auroras can outshine the star in radio wavelengths. Bow shocks form where the stellar wind hits the field, while magnetic tails stretch for millions of kilometers. These supermagnetized worlds reveal what lies beneath their clouds. A field that strong hints at metallic hydrogen, salty oceans deep underground, or massive conductive cores. When such a planet swings close to its star, magnetic interactions can heat its upper atmosphere and shift the color of its auroral glow. By listening to its radio murmurs and watching its ultraviolet flashes, astronomers learn to weigh the hidden hearts of distant worlds. Other solar systems surprise us with not just one asteroid belt, but several. These belts form stacked rings of leftover building blocks, each with its own temperature and chemistry. Warm inner belts hold rocky debris, while colder outer belts contain ices and organic-rich fragments. The gaps between them aren't mistakes, but signatures of unseen planets clearing paths or locking dust into rhythmic patterns. Every belt is an archive, a timeline of interruptions, collisions, growth spurts, and stalled worlds that never fully formed.
dust smashed from countless impacts glows in infrared, outlining the architecture like chalk lines etched into the dark. Some solar systems orbit stars so small and faint you'd miss them at a glance. These tiny red embers are everywhere in the galaxy, and many cradle planets. Their disks are compact but long-lived, giving small worlds plenty of time to grow. A planet orbiting close to such a star might receive enough warmth to remain temperate, even though the sunlight would appear dim and deeply red. Young red dwarfs flare wildly, but over long stretches they settle down, allowing thick atmospheres or magnetic shields to survive. Because these stars are so common, their planets may make up the majority of habitable real estate in the galaxy. Their frequent transits help astronomers map atmospheres, seasons, and sometimes even weather patterns. Under their crimson noon, the parent star would loom large and steady, bathing the surface in warm, ruddy light. Small stars make big possibilities. Some planets go even further and orbit inside stellar winds. Every active star exhales a river of charged particles, and certain worlds wander so close that their skies are carved by the constant storm. At the boundary where the planetary field meets the stellar wind, shock fronts bloom, lighting up the poles with massive auroras. The wind strips gases, shapes plasma tails, and can even drive electric currents that heat the upper atmosphere from within. These harsh conditions reveal a planet's strengths and weaknesses, whether it has a magnetic field, how dense its air is, and what volatiles hide within. As the star cycles between calm and fury, the planet responds in rhythms of light and chemistry. Watching these interactions is like observing a conversation between star and world. Some planets even trail comet-like tails. Their atmospheres evaporate so quickly under intense heat that long streams of gas sweep behind them, curved by orbit and pushed outward by starlight. The tail begins blocking the star's light before the planet arrives and continues after it moves on, creating a long, dramatic transit. Different colors of light are absorbed at different points in the tail, allowing astronomers to map the escaping gases. These streams break into clumps, fade, and regrow depending on the winds of the star. They are living records of atmospheric escape, showing in real time how a sky can thin, breathe out, and disappear. And then there are planets orbiting black holes. These planets don't cling to a sun's warmth, but to gravity itself. They may be lit by a distant companion star or by the eerie glow of an accretion disk spiraling toward the black hole. Their orbits must be wide enough to avoid being torn apart, yet tight enough to remain bound amid the jostling gravity of nearby stars. Evidence comes in subtle pieces: gravitational lensing events that flicker for seconds, or ripples in accretion disks shaped by an unseen companion. If radiation levels remain low and conditions stable, these planets and even their moons could endure for eons. In these distant realms, the ruler is gravity alone, and survival means learning the quiet geometry of space-time. Some planets never experience night. They rotate so slowly or become tidally locked that one hemisphere lives forever under blazing daylight while the other lies in frozen shadow. On the day side, the sun never sets, shifting only slightly across the sky over years. Heat builds endlessly, driving towering storms and winds that churn without rest. Life, if it evolved here, would grow beneath a sky of permanent noon. Only the thin twilight ring between the extremes offers refuge, a narrow world where day and night meet in uneasy balance. These planets remind us that Earth's rhythm of sunrise and sunset is not universal. Some worlds live in eternal day, never knowing the peace of darkness. Others glow from within. Young or massive planets pour out so much internal heat that they shine faintly in infrared or even visible light. Some are still cooling from violent births, their interiors roiling with molten rock and crushed metals. Others are heated by tidal forces, squeezed and stretched by nearby giants until their energy seeps outward. Their surfaces may host molten lakes, glowing atmospheres, and shimmering clouds of vaporized elements. To a distant telescope, they appear as miniature stars orbiting larger ones. With time, they cool and fade, settling into quiet obscurity. But for millions of years, they blaze with the fire of youth. And many solar systems never clear away the dust of their birth. Long after planets have formed, clouds of microscopic grains fill the space between them, glowing in infrared and tracing arcs sculpted by hidden worlds. In young systems, the dust is so thick it turns everything into a warm, smoky haze. It captures the stories of collisions, migrations, and moons taking shape. In older systems, the dust becomes a soft echo of ancient chaos, made visible only when starlight threads through it. These drifting grains remind us that planetary systems aren't static. They grow, shift, collide, and rearrange even long after planets have settled into their orbits. Planets can even form in the shadows of giant blazing stars. Massive stars burn fiercely, stripping and melting nearby materials. But behind dense clumps of gas or within protected eddies, little pockets of calm appear. Dust grains cling together, ices coat tiny pebbles, and larger bodies slowly assemble, shielded from the worst radiation. Even in the light of a star millions of times brighter than the sun, creation finds a way.
From the edges of the galaxy to the shadows of dying stars, the universe keeps reminding us that planets can form, evolve, and vanish in ways far stranger than we once imagined. Every discovery widens the map of what a solar system can be, and the deeper we look, the more extraordinary the possibilities become. Some planets may be born in environments sculpted by ancient supernovas or forged near extreme stars, where tides and pressure twist matter into unfamiliar forms. We haven't yet traveled to those distant regions, but their gravity, their strange behavior, and the scars they leave on nearby starlight show that nature builds worlds with far more creativity than our small neighborhood suggests. Astronomers have even witnessed signs of planets being swallowed by their stars. As some stars grow old, they expand enough to brush against nearby worlds. Gas spirals inward, leaving chemical fingerprints in the star's atmosphere. Sudden boosts of lithium or iron appear, elements that normal stellar processes never produce. Some stars even rotate faster than they should, spinning like they've gained momentum from a recent planetary meal. Around white dwarfs, the story continues. These faded stellar embers show heavy elements on their surfaces, even though those elements should sink quickly. The only explanation is a constant drizzle of planetary debris raining down from disrupted orbits. Infrared glows from hot dust rings and flickering dips in starlight fill in the rest of the picture. What we see is not one dramatic ending, but many. Gravity eventually reclaims what it once allowed to roam free. Some planets take their extremes even further, boasting magnetic fields far stronger than Jupiter's. Deep, turbulent interiors behave like colossal dynamos, generating shields of magnetism so vast they can outshine their stars in radio wavelengths. Their magnetospheres stretch for millions of kilometers, forming shock waves in the stellar wind and auroras the size of continents. These magnetic giants reveal what their hearts are made of, whether it's metallic hydrogen or oceans wrapped around super-Earth cores. When such a world sweeps close to its star, magnetic tension can even heat its atmosphere and alter the chemistry of its glowing poles.
By listening to their radio whispers and watching ultraviolet flashes, we uncover the hidden machinery inside distant worlds. Some solar systems host not one, but several asteroid belts. Stacked like cosmic rings, each belt holds different temperatures and ingredients. Warm inner belts brim with rocky fragments, while cold outer belts hide ice and organic materials. Gaps between those belts reveal the silent work of planets shaping the debris, carving lanes or locking grains into resonant patterns. Collisions grind larger bodies into dust that glows in infrared light, outlining the system's architecture. In youthful systems, that dust brightens and fades as smash-ups occur. In older ones, the belts linger as archives of long-vanished worlds. Planets also form around stars too faint for human eyes. These small, cool stars glow like red embers, yet host an abundance of planets. Their disks are compact and long-lived, giving tiny worlds time to grow. Though their light appears dim and crimson, long-term stability allows dense atmospheres or strong magnetic fields to survive flaring youth. Because these stars are common, their planets make up most of the galaxy's potentially habitable real estate. Frequent transits let astronomers map their atmospheres and even glimpse shifting weather. Under a red-lit sky, the parent star would loom large and steady. Small stars create enormous possibilities. Other planets orbit so close to their stars that they sit directly inside stellar winds. These worlds are carved constantly by streams of charged particles. Shock fronts erupt where the wind meets the planetary field, triggering auroras that wrap entire hemispheres. Winds strip gases, sculpt plasma tails, and generate electric currents that heat the upper atmosphere. Each world's response reveals whether it has a magnetic field, how dense its air is, and what chemicals are present. Watching these interactions is like witnessing a dialogue between star and planet, a full circuit of energy from stellar heartbeat to planetary glow. Some planets trail comet-like tails. Extreme heat can tear gas from their atmospheres, shaping long glowing streams pushed outward by starlight. When these planets transit their stars, the tail dims the light before and after the planet itself, stretching the event into a drawn-out signature. Different wavelengths reveal different ingredients and expose how conditions shift over time. These tails fragment, fade, and regenerate as stellar winds change. They are living records of atmospheric escape. We've even found planets orbiting black holes. Bound not by warmth but by gravity, these worlds circle cosmic darkness. Daylight might come from a distant companion star or from the glow of hot gas swirling around the black hole. Their orbits must remain wide enough to avoid tidal destruction, but tight enough to stay anchored despite passing stars. Evidence comes in hints, lensing events, distorted disk patterns, flickers of light. Yet even here, stability is possible. If radiation is mild and tides are gentle, atmospheres and moons can survive for astonishing lengths of time. In these remote regions, gravity is king, and planets endure by learning its deep geometry. Some planets never see night at all. Tidally locked or slowly rotating, they live in perpetual daylight on one side and eternal darkness on the other. On the day side, the sun never sets. Heat soars, clouds tower, winds churn through endless convection. Life, if it arises, must adapt to ceaseless light. Only the thin twilight band in between offers a balance of warmth and cold. These worlds show that the day-night rhythm we take for granted is not universal. Other planets glow with their own heat. Young or massive giants radiate so strongly from within that they shine in infrared or even faint visible light. Some are still cooling from violent births. Others are squeezed and stretched by tidal forces, generating heat through friction. Molten lakes, glowing clouds, and vaporized minerals shape their landscapes. For millions of years, these planets burn like miniature stars before settling into darkness. Many solar systems stay filled with dust long after their planets form. Fine grains, shattered rocks, and comet fragments scatter starlight into hazy glows. This dust reveals hidden planets, ongoing collisions, or drifting debris. Some systems are so thick with dust that they resemble warm fog. Others carry only thin traces of past destruction. Planet formation can even occur in the shadows of giant stars. Massive stars radiate hard enough to melt or blow away nearby material, yet sheltered regions behind disks or clumps of gas provide safe pockets where planets can quietly grow. Pebbles stick, ice forms, and worlds slowly take shape despite the blazing environment. When the parent star finally explodes, surviving planets may carry exotic materials forged in the last moments of its life. These are survivors of stellar fire. Some worlds are slowly eaten by their star's radiation. Their atmospheres peel away atom by atom, drifting into space like cosmic smoke. Lighter elements escape first, heavier ones later. Over eons, these planets shrink, lose mass, and transform. Some fade entirely, leaving only bare cores or faint dust rings behind. Erosive stellar winds turn whole planets into fading memories. Other systems capture interstellar visitors. Wanderers thrown out of their original solar systems drift for ages until a new star's gravity traps them. Their strange orbits and unfamiliar chemistry reveal origins from far away. Some stay, some leave again. Their presence proves that even planets can migrate between stars. In some disks, giant gases form in just a few thousand years. Instead of growing slowly, entire regions collapse in sudden gravitational instabilities, creating worlds in one cosmic leap. These fast-forming giants disrupt their disks, migrate rapidly, and reshape entire systems before they even settle. Solar systems can also arise from the ashes of supernovas. Heavy elements scattered by the explosion enrich new clouds with iron, gold, uranium, and complex chemistry. Planets born in these disks begin life packed with metals and radioactive heat sources. Even Earth may be such a descendant, carrying traces of ancient stellar death. We've even found signs of planet formation near black holes. If a newborn star forms close to one, its disk may still gather material into growing planets. Gravity stretches and compresses the disk, but formation continues if stability emerges. These planets orbit a star that orbits a black hole, experiencing layered motions and tidal stresses. Even here, worlds can rise. Some planets are too hot for matter to stay solid. Close to their stars, rock vaporizes, iron liquefies, and crust becomes a boiling ocean of minerals. Atmospheric cycles resemble those of stars more than planets. Vapor turns to molten rain, hardens into dark glass, then slides back into lava. These worlds redefine what a planet can be. Others lose their atmospheres entirely, stripped away by heat or weak magnetic.
A single misstep on some worlds would feel like a sudden drop, with gravity tugging far harder than anything we're used to on Earth. These planets carry the scars of ancient cosmic collisions, reminders that creation isn't always gentle. Sometimes entire worlds are born from the shattered remains of others. But not every solar system forms the way ours did. While we treat ice as a common ingredient, especially in the outer regions filled with comets and frozen bodies, some star systems never develop it at all. Their birth environments might be too hot, too crowded, or too turbulent for ice to ever solidify. Other systems orbit stars that blast out so much radiation that frozen materials evaporate long before planets can capture them. In these scorching, iceless systems, every world is rocky or metallic, stripped of the frozen reservoirs that help regulate temperature or deliver water through impacts. Without ice, atmospheres may be thin or completely missing, oceans never appear, and even distant planets remain dry, dusty, and sun-scorched. These barren systems challenge our assumptions about how essential ice truly is. They show that water, so abundant on Earth, is far from universal. Then there are the planets with weather on a scale that almost breaks the imagination.
Some of these worlds host storms bigger than Earth itself. Driven by intense heat, rapid rotation, or deep atmospheric layers, a single storm can wrap around an entire planet, with winds racing thousands of kilometers in one cycle. These tempests may rage for centuries, fueled by internal heat or unending sunlight. Lightning crackles through cloud decks hundreds of kilometers thick, flashing like slow, rolling fire. Jet streams twist into towering vortices near the poles, endlessly recycling energy. On some of these planets, the idea of a calm day simply doesn't exist. The sky is always alive, always shifting. These giants reveal the incredible physics that shape atmospheres not only on gas giants, but on super-Earths and molten terrestrial worlds. And the surprises don't stop there. Some solar systems even contain adopted planets. These are rogue worlds, born in one star system, but violently flung into interstellar space, doomed to wander in darkness for millions or billions of years. If one of these drifters passes near a star with just the right gravitational pull, it can be gently captured and placed into a new orbit. These adopted planets often carry chemical fingerprints from their original homes, making them stand out among their new neighbors. Their orbits may be wildly tilted or stretched, clear evidence of their turbulent past. Over time, they may settle, or they may drift again. Their existence proves that solar systems aren't static. They can trade planets across the galaxy like cosmic travelers switching homes. Other systems orbit stars so faint you could never see them with the naked eye. Brown dwarfs and dim red dwarfs emit almost no visible light, yet they still gather disks of dust and gas capable of forming planets. Planets around these stars live beneath dim skies and low heat levels, even when orbiting extremely close. Some are frozen solid, while others stay warm thanks to thick, insulating atmospheres. These tiny stars burn slowly and live far longer than our sun, offering their planets billions upon billions of years of stability. They show that you don't need a bright star to build an entire planetary family. Even the faintest glow can shape worlds. Many solar systems are also wrapped in enormous clouds of comets, stretching light years beyond their outermost planets. These clouds, made of trillions of icy fragments, are leftovers from the chaotic era of formation. They move in slow, ancient orbits, drifting at extreme distances from their stars. Every so often, one is nudged inward, sending a comet on a long journey past the planets. These icy visitors may deliver water, organic materials, or essential elements, but they can also bring destruction with a single impact. Though invisible in most wavelengths of light, these colossal clouds mark the true outer edge of a solar system. They are frozen history waiting to be awakened. And finally, some planets orbit in paths so extreme they wrap over the poles of their stars. While most planets follow the same direction as the rotating disk that formed them, a few break the rules entirely. Instead of circling like wheels rolling across a table, these worlds loop vertically, crossing high above the star's north and south poles like spinning tops standing upright. These polar orbits challenge everything we thought we knew, revealing just how wildly diverse solar systems can be.
Some planets follow nearly vertical orbits because of past gravitational chaos. A close brush with another planet or the passing tug of a nearby star could have yanked their paths upright, pushing them into strange, almost 90-degree loops. These steep orbits expose them to unusual patterns of sunlight, causing extreme seasons and radiation levels that shift wildly throughout the year. These polar trajectories remind us that the universe isn't limited to neat, flat arrangements. Gravity can twist orbits into unexpected shapes, showing just how creative cosmic architecture can be. Not every star ends up with planets at all. While many begin life surrounded by swirling disks of dust and gas, some systems fail to form even a single world. Their disks may be ripped apart by strong stellar winds, evaporated by harsh radiation, or simply lacking the solid materials needed to build planets.
Sometimes the neighborhood is far too crowded, and the gravitational influence of nearby stars disrupts planet formation before it even begins. These empty systems may look calm today, but they lived through a turbulent childhood where nothing survived long enough to grow. A few grains of dust may linger for millions of years, but they never become anything more. These silent, planetless systems are reminders that creation takes not only ingredients, but also timing and luck. On the opposite end, some young disks contain far more dust than gas. Most planetary nurseries are gas-rich, allowing giant planets and thick atmospheres to develop. But dusty disks tell a different story. They may be the aftermath of violent collisions, shattered protoplanets, or the remains of long-lost worlds. In these environments, new planets form quickly from dense, dry material. They grow into rocky or metallic giants, but lack the gases needed to build atmospheres or gas giants. These worlds stand exposed to space, shaped by a recipe that begins not with air and ice, but with the broken bones of older systems. We've also discovered planets that orbit unbelievably far from their stars. Some circle at distances thousands of times greater than Earth's orbit, taking millions of years to complete a single loop. At those distances, the star's gravity is barely strong enough to hold them. A passing star, a drifting gas cloud, or even the galaxy's faint gravitational tide could push them loose. These distant worlds might have been born close to their stars and slowly migrated outward. Or perhaps they were captured from interstellar space and are only loosely tethered to their new home. They blur the line between belonging and drifting, forcing us to ask a deeper question: where does a solar system truly end? Among the strangest discoveries are planets that look suspiciously artificial. A handful of exoplanets show patterns, structures, or signals that don't quite fit natural explanations. Some appear almost perfectly shaped when nature should produce uneven worlds. Others dim their star's light in repeating geometric ways, as if blocked by panels, segments, or massive engineered structures. Of course, natural explanations exist: clouds of debris, shattered moons, unusual atmospheres. But the possibility remains that a few objects out there might be artificial megastructures. This curiosity has pushed scientists to develop new tools to look for unusual chemical signatures, engineered shadows, or orbits that only make sense with active propulsion. No artificial planet has ever been confirmed, but the fact that we're asking the question shows how far our imagination and technology have grown. The universe might hold not just worlds, but wonders built by ancient minds. Some star systems simply don't give planets a chance. Binary and multiple star systems are common, but some pairs orbit each other so closely or so chaotically that no stable region exists for a planet to survive. In these environments, worlds would be torn apart or flung away before they could ever finish forming.
In some star systems, planets don't stand a chance. When two stars orbit each other too closely, their combined gravity becomes a destructive tide. Any object caught between them can be ripped apart, swallowed by one star, or flung into space at tremendous speed. Even if a planet somehow forms at a safe distance, the shifting light and heat from both stars can swing wildly, creating temperature extremes that make stable geology or long-lasting atmospheres nearly impossible. These chaotic systems show us the hard limits of planet formation. The universe creates worlds often, but not always. Sometimes the dance of multiple stars is so fierce that nothing else can survive. We've also found planets that literally evaporate over time. These worlds orbit so close to their stars or are made of such delicate materials that they slowly dissolve into space. Their surfaces vaporize, forming long, ghostly trails of gas that drift behind them like burnt shadows. Some lose thousands of tons of atmosphere every second, shrinking as the years pass until only a dense, rocky core remains. Astronomers detect these evaporating planets by watching their size decrease or by observing traces of vaporized rock and gas drifting near the star. They prove that even a stable orbit isn't always safe. A world can survive for billions of years only to fade grain by grain into the cosmic wind. Other planets are newborn and far too young to have solid surfaces. These worlds remain molten for millions of years after formation. Heat from collisions, radioactive decay, and leftover energy from their birth keeps their surfaces churning like pools of glowing liquid. They shine faintly in infrared, like embers simmering in the darkness. Their atmospheres are thick with steam, rock vapor, and sulfur gases, forming clouds made of molten metals and glass. Material still rains down as these planets swallow smaller bodies that strike their molten surfaces. Only with time does the glow cool, allowing a crust to harden and oceans or continents to form. These fiery worlds offer a glimpse into Earth's own origins, when our planet was a glowing sphere spinning beneath a dark sky, waiting for its first stone crust to settle. Some star systems, on the other hand, are arranged with astonishing symmetry. Planets line up in perfect ratios. Moons orbit in repeating patterns. Their orbital periods lock into rhythms that repeat like cosmic clockwork. These elegant configurations aren't accidents. Over billions of years, gentle gravitational nudges push planets into stable, balanced arrangements that minimize chaos. These systems can endure for ages, surviving stellar evolution and passing objects without falling apart. Their beauty lies not just in their appearance, but in the mathematics behind them, showing how the laws of physics naturally weave order into motion on truly enormous scales. Then there are planets with oceans made not of water, but liquid carbon dioxide. On worlds with the right pressure and temperature, carbon dioxide behaves as a dense, flowing liquid that gathers into vast seas. These oceans may stretch across hemispheres, shimmering beneath layers of frozen fog. Below the surface, heat and pressure dissolve exotic chemicals, creating conditions where life could exist in forms we've never imagined. Volcanoes may spew fountains of liquid CO2 that fall back down as freezing rain. Waves may carry chunks of mineral ice instead of water. These planets remind us that oceans come in many forms, and habitability does not always look like sunshine and blue waves. Finally, some planets orbit their stars on paths so enormous that a single year lasts more than 1 million Earth years. These distant giants move so slowly that their parent star appears as little more than a bright point in their sky. They receive almost no warmth from starlight, relying instead on internal heat left over from their formation. Made mostly of ice and rock compressed under immense pressure, their surfaces and atmospheres evolve at glacial speed. The gravity of nearby stars or even the galaxy itself can gradually reshape their orbits over millennia, stretching them into long, drifting arcs. These worlds challenge our sense of time. During one of their colossal years, continents could rise and erode away, atmospheres could transform, and entire civilizations could appear and vanish before the planet completes a single lap around its star. Some worlds remind us that time itself bends and stretches depending on how fast they move. Their rhythms make Earth's entire history feel tiny. In distant solar systems, astronomers have found planets so heavy that ordinary rock simply cannot explain them. Their densities are far beyond anything our planet can create. These ultra-dense worlds likely contain exotic materials squeezed into forms that don't exist naturally on Earth. Some may even be built from degenerate matter, similar to what lies inside the cores of dead stars, or forged from the remnants of giant planets shattered long ago. Their gravity is overwhelming. Atmospheres collapse close to the surface, creating boiling oceans of gas or metallic rain. Deep inside, pressures climb so high that atoms fuse into strange lattices and new phases of matter.
These planets are cosmic anvils, shaped under extreme violence during the earliest days of their solar systems or in catastrophic collisions. They remind us that there's no single blueprint for making a planet. Some are simply too dense, too strange, and too ancient to fit any familiar category. And planets don't always begin as planets. Sometimes they're born from chaos. When two large moons smash into each other, the impact hurls molten rock and debris into space. Over time, these fragments merge and cool, forming a brand new world with a composition unlike anything around it. These collision-born planets may lack key elements found in their parent stars, or contain odd mixtures of silicate and metal from both original moons. Their orbits often tilt or wobble, echoing the violent event that created them. They represent a second generation of world building, proof that even destruction has a role in cosmic creation. Solar systems themselves are not permanent structures. Over billions of years, they stretch, shift, and reshape as gravity, stellar winds, and outside forces tug them into new patterns. As stars lose mass, their grip weakens, allowing planets to drift outward into colder, quieter orbits. Passing stars or drifting clouds can nudge comet swarms inward, scatter moons, or alter asteroid paths. Even planets within the same system can slowly push each other into new positions. These changes happen so gradually that no planet survives long enough to witness the full transformation. Stability in space is only temporary. The night sky's calm appearance hides a universe that is always in motion. Not all planets are dense and heavy. Some are astonishingly light. A class of worlds called superpuffs are so airy that if they could be placed in a large enough ocean, they might actually float. They're often the size of Jupiter, but contain only a small fraction of its mass. Heat and low gravity stretch their atmospheres into giant balloon-like shells that rise thousands of kilometers above their cores. Sunlight filters through these thin layers, giving astronomers clues about their chemical makeup. Superpuffs may have formed near hot stars that inflated them before they could contract, or they may have drifted outward to preserve their delicate structure. They challenge all our expectations about density, reminding us that not every planet is a solid, weighty sphere. Some float like cosmic balloons in the vast darkness. In other systems, time barely moves at all. Some planets orbit so far from their stars that a full year takes hundreds of thousands of years or more. On such worlds, daylight changes so slowly that entire civilizations could rise and fall before the planet completes even a small fraction of its orbit. Seasons last millennia. Temperature shifts stretch across geological eras, not years. These distant worlds sit far from stellar storms, but face constant exposure to cosmic rays and drifting clouds of interstellar dust. If life exists there, it would evolve without sunlight or rapid change. For these planets, a year is not a cycle, it's an entire epoch. And then there are the planets we almost never see. Some hide behind their stars for most of their orbit, invisible in the overwhelming glare. We detect them only through the slightest gravitational tugs, faint dips in starlight, or subtle disturbances in nearby planets. Their orbits are positioned so precisely that the star masks them almost perfectly. Only the most delicate clues reveal their presence. These hidden worlds remind us that space is full of secrets. Even when we think we understand a solar system, there is always something waiting quietly in the light.
These hidden planets remind us that our view of the universe depends entirely on the angles we observe and the limits of light itself. Much of the cosmos is shielded by its own brightness. Entire worlds could stay invisible for ages unless we learn to recognize the faint traces they leave behind. Some solar systems contain planets that never see their own sky. Thick layers of clouds or dense atmospheric haze block every glimpse of the outside universe. Their surfaces lie beneath a permanent veil, glowing faintly or wrapped in dim shadow. There are no stars, no moonlight, no constellations to guide the eye.
Day and night blur together in an endless fog. On some of these worlds, boiling clouds of sulfur or carbon-rich gases rise and fall in toxic waves. Others are bitterly cold, choked by methane smog that never clears. If life ever arose on such planets, it would have no awareness of the cosmos. Generations would live and die beneath that ceiling of mist, unaware of the stars that lie just beyond it. These sealed worlds remind us that not every planet shares our wide-open sky. Some live entirely inside their own atmosphere, with wind and weather as their only reference to the outer universe. We've also discovered solar systems forming inside binary star systems. In these regions, two suns orbit each other while planets take shape around them. The tug of both stars creates complex gravitational patterns, sculpting the surrounding dust into unusual shapes. Some planets orbit both stars in broad, stable loops, watching twin sunrises arc across their skies. Others circle just one star, while the second glows as a bright, shifting companion. Their tilted orbits, dense asteroid belts, or broken disks show how double star systems create possibilities far beyond the familiar. Not every solar system is built around a single source of light. Some were born from dancing pairs, where balance emerges from the pull of two suns. But stars don't just influence their own planets. Sometimes they steal them. In crowded star clusters where many suns live close together, stellar encounters can cause one star to tug a planet away from another, capturing it like a silent thief. A planet may be snatched into a new orbit, carrying the chemical fingerprints of its original star. Others are flung into deep space, wandering as rogue planets with no sun at all. These gentle but powerful exchanges show that solar systems aren't isolated kingdoms. They constantly trade, lose, and rearrange planets in the drifting motion of the galaxy. Nothing in space is truly owned. Everything is temporary. Even more surprising, planets can form in places colder than any winter on Earth. In the farthest reaches of space, where starlight barely reaches, disks of pure ice can form around young stars or even around planets themselves. These disks are made mostly of frozen water, methane, and carbon dioxide. There is almost no dust or metal. Gentle collisions fuse icy grains together, gradually building larger fragments which eventually grow into solid worlds. These ice-borne planets begin as frozen sculptures, some remaining frozen for billions of years, others thawing as they migrate inward. Some may even develop underground oceans if internal heat melts their lowest layers. These ice-borne planets show that not every world begins with fire. Some are created from the quiet frost of interstellar space. And then there are the truly strange systems, those that contain tiny black holes. In rare cases, a newborn star forms near the leftover corpse of a long-dead giant. A small black hole can settle peacefully inside the system, its gravity subtle but ever-present. These miniature black holes may be relics from ancient explosions or collapsed stars from an earlier cosmic era. They shape the orbits of planets, clear gaps in surrounding debris, and sometimes give off faint X-ray whispers as they gather particles of gas or dust. A solar system built around both a shining star and a lingering black hole challenges everything we think we know. It shows that cosmic history can overlap, with the living and the dead sharing the same gravitational stage. We've even found planets that exist as endless seas of molten rock. Some orbit so close to their stars or formed in such violent conditions that their surfaces never cool. Temperatures soar high enough to vaporize metals and turn solid stone into glowing rivers of lava. Entire worlds, forever burning, forged from heat and fury.
These worlds often lack an atmosphere entirely because gases cannot condense or remain bound in such overwhelming heat. Any exposed surface melts instantly, flowing like liquid metal as tides of lava shift and pulse beneath the pull of nearby gravity. Viewed from space, these planets glow in infrared light, their molten skin shimmering like embers inside a furnace. Some may eventually cool if they drift far enough from their stars, but many remain locked in eternal fire. These blazing planets remind us that the universe does not promise comfort. Some worlds are not built to evolve or host life. They are made to burn, endlessly and silently. Not every solar system begins with water. While our own is rich with ice and oceans, many stellar nurseries form in dry corners of space, where hydrogen is abundant but oxygen is scarce. In these regions, planets emerge from dust, metal, carbon, and silicates, without the icy delivery systems that bring water later. Such planets have no clouds, no rivers, no oceans, and no landscapes softened by erosion. Their surfaces are raw and jagged, sculpted by volcanic activity and wind-driven sand. If life ever takes hold, it must rely on strange solvents or mineral-based chemistry rather than water. These waterless worlds show that Earth's conditions are far from universal. Many planets may never feel rain or experience storms or carve valleys with flowing liquid. Their beauty lies in fire and stone, not water and weather. Some solar systems form at the very edge of interstellar space. Not every world is born near a warm, glowing star. In the dark outskirts of molecular clouds, where starlight is faint and gravity is gentle, particles drift slowly and collide softly. Over millions of years, they stick and grow without ever being vaporized by heat. The planets that emerge are small, icy, and incredibly slow-moving. Their parent stars are so distant that warmth and light take centuries to reach them. Even at midday, their skies stay dim and muted. Yet beneath their frozen crusts, pockets of warmth may persist, fueled by internal radioactivity or pressure from accumulating mass. These edge-born planets prove that worlds can take shape in shadows, patiently forming in places where sunlight may never come. Some solar systems hide entire inner regions from their own stars. Thick rings of dust or gas can block starlight, casting planets into permanent twilight. These worlds survive on faint, indirect warmth or the lingering heat from their formation. They never experience true daylight. Their skies remain dull, hazy voids without clear shadows or starry nights. Eventually, these dust rings may drift outward or burn away, revealing the star in sudden bursts of light that transform surface conditions. But while the darkness lasts, these planets exist in near silence, untouched by the solar energy that shapes climates and weather on Earth. These shadowed systems remind us that even with a star at the center, light is never guaranteed. We've even detected planets stretched into the shape of footballs. Although gravity usually pulls worlds into near-perfect spheres, extreme tidal forces can distort a planet into a long, bulging oval aligned with the source of the pull. From afar, these planets look like cosmic ovals with swollen equators and compressed poles. Their crusts strain under the stress, triggering eruptions, quakes, and oceans that surge endlessly under gravitational pressure. Their atmospheres thin where the planet is stretched and thicken where it is squeezed, creating rapid, chaotic weather. If these planets drift farther from the force deforming them, they may eventually round out again. Or they may break apart entirely, leaving behind rings of debris. These worlds show that even one of the most basic rules of planetary shape can be bent when nature applies enough pressure. Some solar systems form around stars too massive to survive long. These colossal suns burn so fiercely that they exhaust their fuel within a few million years. Yet during their short lives, their surrounding disks can still create planets. These worlds are doomed from the start, destined to be destroyed when their parent star explodes in a supernova. But until that moment, they can host giant planets, molten moons, and glowing rings stirred by intense radiation. Life is unlikely in these violent environments, yet the brief existence of such planets still echoes through cosmic time.
When these stars erupt, they scatter heavy elements across the galaxy, seeding the material for future solar systems. These brief star-born worlds remind us that not every cosmic story is long-lived. Some shine brightly and vanish, creating and destroying planets in the span of a single cosmic heartbeat. And then there are solar systems so young that their planets still glow.
In some distant solar systems, every known planet is strikingly similar in size, almost as if they were poured from the same cosmic mold. Instead of a mix of giants and runts, these families consist of tightly packed super-Earths or mini-Neptunes, each only slightly different from the next. Yet despite their shared scale, their personalities can vary wildly. A planet closer to the star might be scorched and stripped bare, while a sibling just a little farther out could be wrapped in thick clouds or layered oceans. This surprising uniformity hints at early conditions that divided material more evenly, or gravitational balances that prevented worlds from outgrowing one another. It's a quiet reminder that normal is a flexible idea in astronomy. The universe might love symmetry far more than we do, and such balanced systems tease the possibility that stability and life-friendly environments could emerge more often when no planet dominates the gravitational stage. Then there are solar systems where planets orbit so close to their stars that metal itself turns to vapor. These ultra-hot worlds complete a full year in days or even hours. Under their relentless suns, temperatures climb high enough to evaporate iron, rock, and minerals. Mountains may never form because the ingredients of stone simply sublimate into the atmosphere. Powerful winds sweep metal vapor from the scorching day side to the frigid night side, where it cools into glittering mineral clouds that could rain molten droplets back to the surface. These planets push chemistry far beyond anything we know on Earth, teaching us how atmospheres behave when heat crosses into extremes. Their very existence proves that planet formation doesn't shy away from the furnace, it adapts, creating strange survivors in places we once thought impossible. Other worlds lose their atmospheres entirely. Not every planet manages to hold on to a sky. Intense stellar winds and radiation can blast gases into space, stripping close-orbiting planets down to bare rock. Without an atmosphere, the day side bakes while the night side freezes in a harsh, silent duel of heat and shadow. There's no weather, no protection from meteoroids, and no medium for sound. Still, these airless landscapes act like perfect record keepers, preserving a planet's geological history without the erasing effects of wind or rain. By studying them, astronomers learn how atmospheres are lost, how magnetic fields shield or fail, and how delicate the balance of pressure and temperature can be. Even without air, these scarred worlds reveal powerful stories about survival. Other planets begin life far from their star and only later move inward. Where a world forms is not always where it ends up. In the cold outskirts of young disks, ices and dust can clump together more easily, building massive cores that eventually drift toward warmer regions. This slow inward journey can happen through gas drag or through gravitational nudges from neighboring worlds. A giant born in deep freeze might end up sizzling close to its star as a hot Jupiter, utterly out of place from where it formed. As it migrates, it can scatter smaller planets, sculpt debris, and lock survivors into resonant rhythms. By tracing these migrations, scientists decode the hidden past of systems that seem calm today. A planet's current orbit is just a snapshot, not a birthplace. Of course, not all solar systems survive forever. Some meet violent ends when their stars explode as supernovas. A massive star nearing death can erupt with a brightness that outshines entire galaxies for a moment. Shockwaves rip through nearby planets, stripping atmospheres, melting surfaces, or shattering worlds entirely. Even planets that remain intact may be sterilized by radiation so intense it rewrites their chemistry in seconds. The blast carves huge bubbles through surrounding gas, ending planet formation nearby, but potentially triggering it far away.
fragments of shattered worlds drift into deep space, becoming lonely remnants of a destroyed system. But even in destruction, a supernova spreads heavy elements that seed future stars and planets. Solar systems die, but their material is recycled into new chapters of cosmic history. Some exoplanets wear rings so massive they dwarf entire stars. Rings aren't just a Saturn exclusive. In a few extraordinary systems, ring structures stretch so wide that their total diameter exceeds that of a medium-sized star. These colossal halos may come from shattered moons, captured comets, or leftover debris that never merged into a satellite. When the planet crosses its star, the rings block light long before the planet itself appears, creating strange dips that first hinted at their existence. Their stability puzzles scientists, because rings that large should quickly spread or crumble. Their persistence suggests recent cataclysms or ongoing processes that keep them in shape. If a moon forms within these rings, it may eventually carve out its own orbit and become a full-fledged companion. Even familiar features like rings can become epic in scale when time and gravity have space to play. Other systems contain moons larger than Earth. These aren't mere sidekicks, but full-fledged worlds in their own right, orbiting giant planets like miniature Earths tethered to colossal hosts. Such exomoons may sustain atmospheres, oceans, and active geology powered by tidal forces from both the planet and the star. Their cycles of light and shadow twist in unusual ways depending on their orbital dance. Detecting them is difficult because their signals blend with those of their planets, but faint timing shifts give them away. If confirmed, they would expand the idea of habitability to include not just planets, but their satellites. A moon with Earth-like mass, protected by a giant planet's magnetic field and warmed by reflected light, could be a surprisingly cozy home. On the other hand, some planets have no moons at all. These solitary worlds travel through space without even a small rock to accompany them. Their loneliness may come from violent early collisions that destroyed their satellites, or from placid births in regions too empty to build them. Without a moon, a planet's tilt can wobble over the ages, causing unpredictable seasons. Tides are weaker, shaping coastlines more slowly, and tidal heating inside the planet becomes minimal. Nights are darker, skies emptier. But these lone worlds offer clean laboratories for understanding geology and climate without external influences. Even the absence of a moon tells a story about scarcity, randomness, and the many paths a planet's history can take. Then there are the strange cases where moons form before their planets. A moon might begin life as an independent object in the swirling disk, or as a captured debris long before the main planet assembles. When the future planet gathers enough mass, it captures the older body into orbit. These ancient moons carry chemical fingerprints unlike their hosts, preserving a snapshot of early disk conditions that the planet itself never experienced. Their surfaces record impacts and radiation from eras before the planet even existed. These mismatched pairs show that order in a solar system is flexible, shaped by timing, capture, and chance. And here's a historic twist. The first exoplanets ever discovered weren't found around stars like our Sun. They were found around a pulsar, the dense, spinning remnant of a dead star. Pulsars emit radio waves with astonishing regularity. Tiny changes in the timing of those beams revealed the gravity of orbiting planets. These worlds survived or reformed after a supernova, enduring in one of the harshest environments imaginable. Their discovery shattered expectations and launched the entire field of exoplanet science, proving that planets can arise in places far stranger than our peaceful solar system. Finally, some planets orbit their stars faster than Earth spins once. These ultra-short period worlds complete a year in mere hours. Locked so tightly to their stars, they are tormented by intense gravity and blistering heat. Their atmospheres can boil away, shift into plasma, or churn in violent cycles. Tidal forces stretch them, melt their insides, and drive fierce volcanic activity. From the surface, the star would dominate the sky,
and daylight would change dramatically in minutes.
From the edges of the galaxy to the shadows of dying stars, the universe keeps reminding us that planets can form, evolve, and vanish in ways far stranger than we once imagined. Every discovery widens the map of what a solar system can be, and the deeper we look, the more extraordinary the possibilities become. Some planets may be born in environments sculpted by ancient supernovas or forged near extreme stars, where tides and pressure twist matter into unfamiliar forms. We haven't yet traveled to those distant regions, but their gravity, their strange behavior, and the scars they leave on nearby starlight show that nature builds worlds with far more creativity than our small neighborhood suggests. Astronomers have even witnessed signs of planets being swallowed by their stars. As some stars grow old, they expand enough to brush against nearby worlds. Gas spirals inward, leaving chemical fingerprints in the star's atmosphere. Sudden boosts of lithium or iron appear, elements that normal stellar processes never produce. Some stars even rotate faster than they should, spinning like they've gained momentum from a recent planetary meal. Around white dwarfs, the story continues. These faded stellar embers show heavy elements on their surfaces, even though those elements should sink quickly. The only explanation is a constant drizzle of planetary debris raining down from disrupted orbits. Infrared glows from hot dust rings and flickering dips in starlight fill in the rest of the picture. What we see is not one dramatic ending, but many. Gravity eventually reclaims what it once allowed to roam free. Some planets take their extremes even further, boasting magnetic fields far stronger than Jupiter's. Deep, turbulent interiors behave like colossal dynamos, generating shields of magnetism so vast they can outshine their stars in radio wavelengths. Their magnetospheres stretch for millions of kilometers, forming shock waves in the stellar wind and auroras the size of continents. These magnetic giants reveal what their hearts are made of, whether it's metallic hydrogen or oceans wrapped around super-Earth cores. When such a world sweeps close to its star, magnetic tension can even heat its atmosphere and alter the chemistry of its glowing poles. By listening to their radio whispers and watching ultraviolet flashes, we uncover the hidden machinery inside distant worlds. Some solar systems host not one, but several asteroid belts. Stacked like cosmic rings, each belt holds different temperatures and ingredients. Warm inner belts brim with rocky fragments, while cold outer belts hide ice and organic materials. Gaps between those belts reveal the silent work of planets shaping the debris, carving lanes or locking grains into resonant patterns. Collisions grind larger bodies into dust that glows in infrared light, outlining the system's architecture. In youthful systems, that dust brightens and fades as smash-ups occur. In older ones, the belts linger as archives of long-vanished worlds. Planets also form around stars too faint for human eyes. These small, cool stars glow like red embers, yet host an abundance of planets. Their disks are compact and long-lived, giving tiny worlds time to grow. Though their light appears dim and crimson, long-term stability allows dense atmospheres or strong magnetic fields to survive flaring youth. Because these stars are common, their planets make up most of the galaxy's potentially habitable real estate. Frequent transits let astronomers map their atmospheres and even glimpse shifting weather. Under a red-lit sky, the parent star would loom large and steady. Small stars create enormous possibilities. Other planets orbit so close to their stars that they sit directly inside stellar winds. These worlds are carved constantly by streams of charged particles. Shock fronts erupt where the wind meets the planetary field, triggering auroras that wrap entire hemispheres. Winds strip gases, sculpt plasma tails, and generate electric currents that heat the upper atmosphere. Each world's response reveals whether it has a magnetic field, how dense its air is, and what chemicals are present.
Watching these interactions is like witnessing a dialogue between star and planet, a full circuit of energy from stellar heartbeat to planetary glow. Some planets trail comet-like tails. Extreme heat can tear gas from their atmospheres, shaping long glowing streams pushed outward by starlight. When these planets transit their stars, the tail dims the light before and after the planet itself, stretching the event into a drawn-out signature. Different wavelengths reveal different ingredients and expose how conditions shift over time. These tails fragment, fade, and regenerate as stellar winds change. They are living records of atmospheric escape. We've even found planets orbiting black holes. Bound not by warmth but by gravity, these worlds circle cosmic darkness. Daylight might come from a distant companion star or from the glow of hot gas swirling around the black hole. Their orbits must remain wide enough to avoid tidal destruction, but tight enough to stay anchored despite passing stars. Evidence comes in hints, lensing events, distorted disk patterns, flickers of light. Yet even here, stability is possible. If radiation is mild and tides are gentle, atmospheres and moons can survive for astonishing lengths of time. In these remote regions, gravity is king, and planets endure by learning its deep geometry. Some planets never see night at all. Tidally locked or slowly rotating, they live in perpetual daylight on one side and eternal darkness on the other. On the day side, the sun never sets. Heat soars, clouds tower, winds churn through endless convection. Life, if it arises, must adapt to ceaseless light. Only the thin twilight band in between offers a balance of warmth and cold. These worlds show that the day-night rhythm we take for granted is not universal. Other planets glow with their own heat. Young or massive giants radiate so strongly from within that they shine in infrared or even faint visible light. Some are still cooling from violent births. Others are squeezed and stretched by tidal forces, generating heat through friction. Molten lakes, glowing clouds, and vaporized minerals shape their landscapes. For millions of years, these planets burn like miniature stars before settling into darkness. Many solar systems stay filled with dust long after their planets form. Fine grains, shattered rocks, and comet fragments scatter starlight into hazy glows. This dust reveals hidden planets, ongoing collisions, or drifting debris. Some systems are so thick with dust that they resemble warm fog. Others carry only thin traces of past destruction. Planet formation can even occur in the shadows of giant stars. Massive stars radiate hard enough to melt or blow away nearby material, yet sheltered regions behind disks or clumps of gas provide safe pockets where planets can quietly grow. Pebbles stick, ice forms, and worlds slowly take shape despite the blazing environment. When the parent star finally explodes, surviving planets may carry exotic materials forged in the last moments of its life. These are survivors of stellar fire. Some worlds are slowly eaten by their star's radiation. Their atmospheres peel away atom by atom, drifting into space like cosmic smoke. Lighter elements escape first, heavier ones later. Over eons, these planets shrink, lose mass, and transform. Some fade entirely, leaving only bare cores or faint dust rings behind. Erosive stellar winds turn whole planets into fading memories. Other systems capture interstellar visitors. Wanderers thrown out of their original solar systems drift for ages until a new star's gravity traps them. Their strange orbits and unfamiliar chemistry reveal origins from far away. Some stay, some leave again. Their presence proves that even planets can migrate between stars. In some disks, giant gases form in just a few thousand years. Instead of growing slowly, entire regions collapse in sudden gravitational instabilities, creating worlds in one cosmic leap. These fast-forming giants disrupt their disks, migrate rapidly, and reshape entire systems before they even settle. Solar systems can also arise from the ashes of supernovas. Heavy elements scattered by the explosion enrich new clouds with iron, gold, uranium, and complex chemistry. Planets born in these disks begin life packed with metals and radioactive heat sources. Even Earth may be such a descendant, carrying traces of ancient stellar death. We've even found signs of planet formation near black holes. If a newborn star forms close to one, its disk may still gather material into growing planets. Gravity stretches and compresses the disk, but formation continues if stability emerges. These planets orbit a star that orbits a black hole, experiencing layered motions and tidal stresses. Even here, worlds can rise. Some planets are too hot for matter to stay solid. Close to their stars, rock vaporizes, iron liquefies, and crust becomes a boiling ocean of minerals. Atmospheric cycles resemble those of stars more than planets. Vapor turns to molten rain, hardens into dark glass, then slides back into lava. These worlds redefine what a planet can be. Others lose their atmospheres entirely, stripped away by heat or weak magnetic.
In their earliest moments, newborn solar systems shine not only with the glow of their young stars, but with the heat of their own creation. Clouds of dust and gas swirl together, warming as they collide, compress, and slowly shape themselves into planets. Even those forming worlds give off their own soft infrared glow, lighting their skies long before they cool into the darker places they will become. These systems are warm cradles of creation, where chemistry races ahead, weather has yet to take form, and surfaces remain molten or unstable. Their light isn't the steady calm of maturity, it's the flicker of beginnings. Through our telescopes, they appear as red-tinted clouds, full of promise, possibility, and the echoes of what our own solar system must have been before oceans formed and crusts sealed away the secrets of early time. As astronomers explore these distant systems, we're beginning to understand just how unusual a world like Earth might be. Many systems lack rocky planets entirely, or contain only giant worlds made of hydrogen and helium. Some orbit multiple stars bathed in harsh radiation. Others are missing vital ingredients like carbon or water. Some are far too young for life to begin. Others are ancient, their habitable worlds already gone. Earth sits in a narrow band of balance, with the right star, the right orbit, the right chemistry, and the right timing for life to grow and endure. Studying other systems doesn't make our home feel smaller. It makes it feel more extraordinary. Among countless worlds, Earth is not just another planet. It is a rare kind of story. Thank you for drifting through the quiet reaches of the cosmos with me tonight. As we wandered from one system to the next, we glimpsed just how strange and beautiful the universe can be. Worlds of fire and ice, stars sharing their light across impossible distances, planets forming, dissolving, colliding, and beginning again. Every system a different tale, every orbit a gentle turning of time. If this soft journey through the stars brought you peace, feel free to like, subscribe, or leave a thought below. It helps other wandering dreamers find their way here, one sleepy soul at a time. But for now, let all that fade away. Let your breathing slow. Let your thoughts drift loose like a comet slipping quietly through the dark. The universe will keep turning without you for a while. You've done enough for today. Close your eyes. Rest. Dream of other skies. Good night.